Alright, so in this lesson we're going to take a look at how to find volumes of solids when we generate them around vertical or horizontal lines using method of cylindrical shells. So far we have used disk method is when we slice it and the cross volume looks like a disk, or we also had washers where it's a disk with a hole inside. So we're going to take a look at something very simple. We're going to take a look at a rectangle, which is basically the area bounded, or the region bounded in by y equals 10, which is the horizontal line, x equals 6, and it's in the first quadrant. So if we rotate it around the y-axis, we basically end up with a cylinder like this. And then it would have the height of 10, because it's going to go up to y equals 10. And then our radius is going to be 6. So there's three methods we can use to find the volume, or at least three methods. We can use geometry. So the volume of a cylinder is the area of the base, which is going to be pi r squared, times the height. So in our case, the radius is going to be 6, and the height is going to be 10. So we don't truly need calculus to find the volume, but this is a great way to check that our answer at the end will be correct. So 36 times 10. So 360 pi would be our volume. So when we start using calculus to set up integrals and using our calculator to find the area, this would be a great way to double check that we are on the right track. Alright, so the first thing I want to do is show you how to use the disk method just to refresh your memory. So what I'm going to do is just draw one disk, which would be representative of a cross-section or cross-section of our cylinder. Not the best drawing, but alright, so we're going to have to slice it horizontally, which means that we would have to use dy, which means that everything needs to be in terms of y. So I know that my limits of integration are going to be in terms of y, so it's going to go from 0 to 10. So I can start setting up my integrals. So it's going to go from 0 to 10, and everything will need to be in terms of y, and we'll come back here. So the good idea would be just to find a volume of this one little cross section. So this is a disk, so the volume of a disk is going to be pi r squared dy. And again, everything needs to be in terms of y. So we notice that our radius doesn't actually change as we move from y equals 0 to y equals 10. So our radius is simply going to be 6 squared. Well, the radius is 6 and it's going to be squared. So it's going to be 36 pi dy. And we just need our 36 pi here. And that's going to be it in terms of setting up our integrals. So we can double check, we don't need a calculator here. The antiderivative of 36 pi would be 36 pi times y. And we're going to integrate it from 0 to 10. And using fundamental theorem of calculus, we'll simply get 360 pi once again, which means that we are on the right track. So then what I'm going to do is I'm going to show you how we can use the shell method, which is the new one, to find the same exact area. Sorry, the same volume. So what I'm going to do is I'm going to erase this, and I'm going to show you, not in this particular example, but just what the shells look like, just so you get an idea what it is we're doing. And let's see. Okay, so I'm going to move this around, and we're going to change this to a little smaller. Okay, so just to give you an idea, here's I have this area, and the solid is going to look something like this. So you can see it from the top. And what I'm going to do is show you what these cylinders look like. So basically we're going to think of this volume as a series of shells. So they look like this. If you take a look at the outside. And I'm going to increase the number of segment, so our shell is a little thinner. So sort of this is the bottom. So instead of having a disk as your cross volume, you have this like one shell, and then the volume is made up of series of shells. So for our cylinder, this is going to be, I'm going to change this to option 3 and use the shell method. Okay. So basically, if you think of your cylinder as just a bunch of shells fitted together, every single shell is going to have the same height. So what I need to do is I need to draw one representative shell. So this is not the best, but you get the idea. So this is going to be one shell. So your shells start from the inner, from inside right around the y-axis, and then they're going to get bigger and bigger and bigger in terms of the radius. So they're just going to keep going, and this would be like your outer shell. Okay. We start in a very similar way. So we try to figure out what would be the volume of this one single shell. And the way that we have the shell tells us that we need to use dx. So everything needs to be in terms of x. Okay, so volume of one little shell. Okay, so if you imagine one of those foam like Coke can holders that go around just to keep it warm, to keep it cold. If you slice it open and you open it up, it literally just looks like a one giant rectangle. And the length of this is going to be the circumference of the circle, so 2 pi r. This would be the height. So 2 pi r h is what you pretty much have to remember. So 2 pi r h would be the area. And then it would either have to be multiplied by dx or dy, depending which way your shells go. So in this case, it's going to be dx here. Okay, so everything needs to be in terms of x. The radius of the shell is basically just going to be the x coordinate. So I'm going to go from 0 to 6. My radius of the first shell is going to be 0, and my most outer radius is going to be 6. So that's going to be my last shell. So the radius is going to be simply just x. The height doesn't actually change. So the height of each shell does not depend on which x value we're using. It's consistently going to be just 10, so I don't need to have an expression for it in terms of x. So I have 2 pi x times 10 times dx, so we're going to simplify that and we get 20 pi x dx. So that basically is the volume of one single shell. So to find the exact volume of the entire solid, we're going to sum up all the volume of these shells. So everything, our radius is going to go from 0 to 6, or the x coordinate, right? So then we have 20 pi x dx. All right, so just to show you that we still get the same answer using this method, what we're going to do is use the fundamental theorem of calculus. So we get 20 pi x squared over 2. And we're going to go from 0 to 6. And 20 over 2 is going to give us 10. So it's 10 pi times 6 squared, which is 36. And as you can see, using this third method, we're still getting the same answer of 360 pi. Now what's going to happen is sometimes you can use the shell method as one of the options. So you can use disks or washers or shells. Sometimes you absolutely have to use shells, and the first example we have would be that particular example. So if we take a region that's bounded by this cubic function and the x-axis, which is this picture right here, and we're going to rotate around the y-axis, if you try to use the disk method, you notice that, I'm just going to draw this real quick, when you would have to define the outer radius and the inner radius, you really can't do that in terms of why? Because you kind of have the same exact function defining both the left endpoint and the right endpoint. So you won't be able to find an expression for the outer and the inner radius in terms of y. So this is a great example where the shell method is absolutely necessary. We already have a picture of one single shell. So remember the volume of one shell is going to be 2 pi RH times dx or dy. So in this case, our shells are going to go this way. So that's going to be my height. That's going to be the radius of the shell. That's going to be the height of the shell. And it's going to look something like this. If I think of opening it up, you could see that it's going to be dx. So everything needs to be in terms of x. Okay. And what's going to happen is this is going to tell you your limits of integration. It's going to go from 1 to 3. All right. So we need to just find our expressions. The radius is an easy one. The radius is going to be simply the x-coordinate because the radius of the smallest shell or the innermost shell is going to be just 1, and then the radius of the outermost shell is going to be just 3. So I know I have 2 pi x. Then I need the height, and the height is simply going to be the y-coordinate in terms of x. So I can just reuse this. So x minus 1 times x minus 3 squared dx. So that's a volume of one single shell. So once I have that, I can set up my volume integral. So it's going to go from 1 to 3. And we have 2 pi x, x minus 1, x minus 3 squared dx. We could multiply this out and use the fundamental theorem of calculus, but on the test you will have a calculator and you'll be able to just simply find the volume once you have the volume set up. So the setup is really the most important thing, and make sure you could actually do that. All right, so we're going to take a look at 2 more examples. Here's example 2. And this would be a problem where if you're given a choice, you can use the disk method because you can slice your volume this way. So use a disk. Or you can also use the shell method, and we can have shells that go this way. So this would be a shell. So this would be everything in terms of y, and then if we use the disk method, everything would be in terms of x. So we're going to use the method of cylindrical shells just to practice. But in a test, if you finish a little early, you could certainly use the disk method to double check that it's correct. Okay, so I'm going to go back and I'm going to draw one single shell. So it's going to look like this. Okay, so here's my radius. Here's my height of the shell. So it's going to be so volume of one shell is going to be 2 pi RH. And in this case, we have dy, because we're going this way. Okay, so now this tells me, so if I have dy, that everything is to be in terms of y. So the radius is going to be just simply the y-coordinate of the point. So as you move here, just the y-coordinate is going to be the radius. The height is going to be, so you have to be careful, it's going to be 8 minus the x-coordinate, right? Because the x-coordinate would give you this distance, we want to use this one. So it's going to be 8 minus x. And we don't want to have x, we want to have everything in terms of y, so we do have to do a little bit of rearranging. So if we cube both sides, we get y cubed equals x. So my height would be 8 minus y cubed. So 2 pi y, 8 minus y cubed dy. So once I have this, I'm done. My volume is going to be, again, so it's a limit of integration for y. So it's going to go from 0 to 2. Right, because it's going to be 0 here, 2 here. And 2 pi y 8 minus y cubed dy. We could certainly find it by hand or by calculator, but I just want to make sure that you can set it up and you can see where things came from. Here's our last example. And I wanted to do this one because you'd have to split up your integral. So the area we have, or the region that we have, is bounded by y equals x cubed, which is this one here, this function. This is a line with a slope of -1/4. And we're going to rotate around, just kidding. We want to rotate around the x-axis, so I'm going to change that. So give me a second. Okay. All right. We can certainly use a disk method here because, the washer, because we would have a hole here. So our outer radius would be defined by the straight line, and our inner radius would be defined by the cube root function. So the washer method would work totally fine. Again, but you might have to use the cylindrical shell method, so let's see how we would do that. So I'm going to draw one single shell. Okay, so if you notice, the height of my shell would be defined by y equals cube root of x up to 2, y equals 2. But then once I go from 2 to 4, my height of the shell is going to change and is going to be defined by the 4 minus 1/4 x function. So I do have to set up two separate integrals. Okay, so how do we do that? Well, let's take a look. So we're going to have everything in terms of y because the thickness of the shell is dy. So volume of one single shell is going to be 2 pi RH times dy, or delta y. Change it to dy to be consistent. Okay. Our radius is going to be the y coordinate. And what's going to change is the height definition. So we'll have to set up two separate integrals. So the first integral is going to go from 0 to 2, and the second integral is going to go from 2 to 4. They're both going to be in terms of y. And for the first one, so we're going to have 2 pi y times the height, 2 pi y times the height. The only thing I need to do is figure out the definition of the height. Okay, so for the shell that's between 0 and 2, the height is going to be the x-coordinate. So I do have to rearrange this, so y cubed is equal to x. So it's going to be times y cubed. And then for my second one, the height is also going to be just the x-coordinate. I just need to change this. So I need to rearrange this, and I'm going to multiply everything by 4. So 4y is equal to 16 minus x, which means that x is going to be 16 minus 4y. So that would be my height in terms of y. So it's 2 pi times 16 minus 4y. But then once you have this set up, you simply find, you set up the integral and you use your calculator to find the volume. And then what I'm just going to do is, just as a review really quickly, we're going to do this, set up the same problem. We're going to use the washer method, because that was something that a lot of you are making a mistake on. So when you find the volume of the washer, I just want to emphasize again, it's pi r squared outer radius squared minus the inner radius squared. So be very careful to square the radius first, because what you're really doing is finding the area of the large circle first, and then you're subtracting the area of the small circle, and then we're simply factoring out the pi. But I had quite a few of you who subtracted first and then squared it, so we want to make sure that you don't do that. Okay, so if I were to go back and do this with the washer method, I'm going to erase this and I'm just going to draw one single washer just to have a good, nice visual. Here's my washer. Not the best washer in the world, but okay. So the outer radius is going to be defined by this function here, and my inner radius is going to be defined by this function here. So before we start, let's do this. So we're going to define the outer radius is going to be the y coordinate. There's going to be 4 minus 1/4 x, and my inner radius is going to be cube root of x. Okay, so the volume of one single washer is going to be pi outer radius squared minus inner radius squared times dx, because we're slicing it this way. And we simply just have to be careful. Let me get this. And I need my dx. So once you have that, we can just set up our integrals. So we're going to go from 0 to 8 because we're slicing it this way. And I'm going to put pi on the outside of my integral. I'm not going to forget my parenthesis. And we get 4 minus 1/4 x squared minus cube root of x squared times dx. So if you were to use your calculator and you would type in the expression for volume using the shell or the washer method, you should get exactly the same answer because you're finding the same volume but just using 2 different methods. Alright, so that was it, and you have plenty of practice from the Stewart book, and keep checking your answers.